In the realm of software development, reliability stands as a cornerstone of excellence, a testament to a system's ability to consistently perform its intended functions without faltering. A reliable software product instills confidence in its users, assuring them that it will operate as expected, without unexpected interruptions or errors. Conversely, unreliable software can lead to frustration, loss of productivity, and even damage to reputation and revenue. Imagine a scenario where an online banking application experiences frequent crashes. Customers attempting to access their accounts or execute transactions are met with error messages and service disruptions. Such an experience would undoubtedly erode their trust in the bank's digital services, potentially leading them to seek more reliable alternatives. This example underscores the criticality of software reliability in today's technology-driven world. Mean time between failures, or MTBF, serves as a crucial metric in assessing the reliability of a software system, providing insights into the average time elapsed between successive failures. It is typically calculated by dividing the total operational time by the number of failures that occurred during that period. A higher MTBF value generally indicates a more reliable system, as it suggests longer intervals between failures. Consider a software application that experiences 3 failures over a span of 1,000 hours of operation. To determine its MTBF, we divide the total operational time, 1,000 hours, by the number of failures, 3, resulting in an MTBF of approximately 333 hours. This implies that, on average, the software can be expected to function without encountering a failure for about 333 hours. Mean time to failure, or MTTF, represents the average time a system or component is expected to operate before encountering its first failure. Unlike MTBF, which considers multiple failures over a given period, MTTF focuses solely on the time until the initial failure. This metric is particularly relevant for non-repairable systems or components, where a single failure renders them inoperable. Imagine a network router that is designed to function continuously until it experiences a hardware malfunction. The MTTF of this router would represent the average time it is expected to operate reliably before encountering this critical failure. Once the failure occurs, the router would need to be replaced rather than repaired. MTTF is calculated by dividing the total operational time of a group of identical systems or components by the number of failures observed. Mean time to repair, or MTTR, quantifies the average time required to restore a system or component to its fully functional state after experiencing a failure. It encompasses the time taken to diagnose the issue, implement the necessary repairs or replacements, and verify the system's functionality. MTTR is a critical metric for assessing the maintainability and resilience of software systems, as it directly impacts downtime and user experience. Consider a web server that experiences a software crash, rendering a website inaccessible to users. The MTTR in this scenario would represent the average time it takes for system administrators to identify the cause of the crash, implement a fix, such as restarting the server or applying a software patch, and bring the website back online. A lower MTTR is always desirable, as it indicates that failures can be resolved swiftly, minimizing user disruption and potential business losses. Availability measures the percentage of time a software system or component is operational and accessible to users over a defined period. It's a crucial indicator of a system's reliability and its ability to consistently deliver its intended services without interruption. High availability is paramount for mission-critical applications, where downtime can have severe consequences, such as financial losses, service disruptions, or even safety hazards. Imagine an e-commerce platform that experiences an hour of downtime due to a server outage. During this period, customers are unable to browse products, place orders, or access their accounts. This outage not only results in lost revenue, but also damages the platform's reputation and erodes customer trust. Ensuring high availability is essential for maintaining customer satisfaction and business continuity. Availability is typically calculated using the following formula. Availability equals total uptime divided by total uptime plus total downtime times 100%. For instance, if a system experiences 2 hours of downtime per month, its availability for that month would be availability equals 720 hours minus 2 hours divided by 720 hours times 100% equals 99.72%. While striving for 100% availability is ideal, it is often impractical or cost-prohibitive to achieve. Failure rate, a crucial metric in software quality assurance, quantifies the frequency with which a software system or component experiences failures over a specific time frame. It provides valuable insights into the overall stability and defect density of the software, enabling development teams to identify areas requiring improvement and track progress in enhancing software reliability. Typically expressed as the number of failures per unit of time, such as failures per hour, failures per day, or failures per million lines of code, failure rate serves as a direct indicator of software quality. A higher failure rate suggests a greater number of defects within the software, while a lower failure rate indicates improved reliability. Consider a software application with a failure rate of 0.05 failures per hour. This implies that, on average, the application is expected to experience one failure every 20 hours of operation. By monitoring the failure rate over time, developers can assess the effectiveness of their bug-fixing efforts and identify any regressions or new defects introduced during development. Failure rate is influenced by various factors, including software complexity. More complex software systems tend to have a higher failure rate due to the increased likelihood of introducing defects during development. Reliability growth represents the ongoing process of improving software reliability over time through a systematic approach to defect detection, analysis, and resolution. It acknowledges that software, even after rigorous testing, may still contain hidden defects that can surface during real-world usage. By embracing reliability growth, development teams can continuously enhance software stability and deliver a superior user experience. The reliability growth model, often depicted as a bathtub curve, illustrates the typical pattern of software reliability over its life cycle. The curve comprises three distinct phases. 1. Early life, infant mortality. This phase, characterized by a high initial failure rate, reflects the presence of readily identifiable defects often discovered during testing. As these defects are addressed, the failure rate decreases rapidly. 2. Useful life, stable operation. During this phase, the failure rate stabilizes at a relatively low level, as most of the major defects have been resolved. Failures occurring in this phase are often attributed to unforeseen usage patterns or external factors. Fault tolerance, a critical aspect of software reliability, refers to the ability of a system to continue operating properly, even in the presence of faults or failures. It involves designing and implementing mechanisms that prevent failures from cascading and impacting the system's overall functionality. Fault-tolerant systems are designed to gracefully handle errors, minimize downtime, and ensure continuous service availability. Imagine a financial trading platform that relies on multiple servers for processing transactions. A fault-tolerant design would ensure that if one server experiences a hardware failure, the other servers can seamlessly take over its workload, preventing any interruption in trading activities. Several key techniques contribute to building fault-tolerant software systems. Redundancy, implementing redundant components, such as servers, databases, and network connections, ensures that if one component fails, a backup component can immediately take over its function, preventing service interruptions. Error detection and recovery, incorporating robust error detection mechanisms, such as checksums, parity bits, and heartbeat signals, allows the system to quickly identify and isolate faults. Recovery mechanisms, such as rollback to a known good state or failover to a backup component, ensure swift restoration of functionality. While each reliability metric provides valuable insights into specific aspects of software quality, it's crucial to adopt a holistic approach that considers the interplay of these metrics to gain a comprehensive understanding of overall system reliability. These metrics are interconnected, and improvements in one area can positively influence others, leading to a virtuous cycle of enhancement. For instance, reducing the failure rate through rigorous testing and bug fixing not only directly improves reliability, but also contributes to a higher MTBF, as failures occur less frequently. Similarly, investing in fault tolerance mechanisms, such as redundancy and failover systems, can minimize downtime and improve both MTTR and availability. A holistic approach to software reliability involves establishing clear reliability goals, defining specific, measurable, achievable, relevant, and time-bound, SMART goals for each reliability metric provides a clear target for improvement efforts. While technical metrics like MTBF, MTTF, MTTR, availability, and failure rate provide valuable insights into software reliability, user satisfaction remains the ultimate validation of software quality. After all, software is created to serve users, and their perception of its reliability directly impacts its success. Users who experience frequent crashes, errors, or downtime are unlikely to consider the software reliable, regardless of its technical merits. Conversely, software that consistently performs as expected, without interruptions or issues, fosters trust and loyalty among users. Measuring user satisfaction with software reliability involves gathering feedback through various channels, such as surveys, conducting regular user surveys to gauge satisfaction with the software's stability, performance, and overall reliability, provides valuable quantitative data. Usability testing, observing users interacting with the software in a controlled environment, helps identify usability issues that may impact their perception of reliability. In today's technology-driven world, software reliability is no longer a mere aspiration, but a non-negotiable imperative. As software permeates every facet of our lives, from communication and entertainment to healthcare and finance, the consequences of unreliable software can be far-reaching, impacting user trust, business continuity, and even personal safety. By embracing a comprehensive approach to software reliability, encompassing rigorous testing, proactive defect detection, continuous improvement, and a user-centric mindset, development teams can deliver software that consistently meets and exceeds expectations. Investing in reliability is not merely a cost, but an investment in user satisfaction, brand reputation, and long-term success in the marketplace. As software continues to shape the future, reliability will remain a cornerstone of excellence, ensuring that technology empowers and enhances our lives, rather than hindering progress with instability and uncertainty.